Hello, everyone. Welcome to today's Moldex3D webinar. I'm Ray Wu, who is account manager from Moldex3D EMEA team. And today our topic is optimal design parameters for injection molded parts using Moldex3D DOE. Okay, so the very first thing I would like to introduce to you is the Moldex3D expert, which is using the DOE in the Moldex3D. So when it comes to the injection molding is a really complex procedure, and it combines like mold design, like part design, the material characteristic, and also the process conditions. And in before, before we have the computer, we usually use the conventional trial and error method to find a way to solve the problem because maybe I have some warpage in the part and maybe I want to solve it. So maybe we will base on the experience or somehow the other ways to like changing the temperature distribution, try to solve the warpage. And that one is based on some theories, but still you don't know yet what is exactly the reason that we have such a problem. And for example, if the warpage comes from the temperature difference, then changing the packing pressure actually do not do any help to the final part. And in that case, maybe it will make it even worse. So with the simulation, actually, we can see why is exactly the reason, and also we can use the simulation to change the parameters to see what would happen if we change these parameters. And with this method, we can save a lot of time in doing the trial and error in the real world, because if you do it in the real world, you would take time, you would take money, and also you need to do the real part. So finally, you'll waste the material. And with the simulation, the only thing you take, we take from you is the time and also the electricity. So it will be more efficient and more like energy savings, I would say, compared to the real world trial and error method. And based on this, we already know that with the simulation, we can improve the product quality. But with the help of the DOE, you can make it even more easier for you yourself, because the DOE actually is like the computer will find the best combination of the parameters that you selected. And based on these selected parameters, we will try to find the best combination for your target. Okay, so what is the expert doing is it's a professional tool that use design of experiment method to help the designer to evaluate the most appropriate gate, like the gate location, the runner size, the optimal process conditions, in order to achieve the best product quality. And relative to the real world, is much more cheaper to have this product in your computer. It's you can talk to your regional manager about the price of it, but I believe it's much more cheaper than you do the trial and error and wasting time to do the trial and error in the real world. Because with the simulation, actually you can run it at home. You don't need to really use the working hours to see what is exactly happens inside the mold. So below you can see like why is the DOE analysis interface, and also it's available in all modules like eDesign, Shell, and Solid. Okay, so here we will go more in depth into the features and the benefit of the DOE. So the very first thing is DOE support both thermoplastic and thermoset material. There's no difference in here in our DOE module. The second thing is we will directly use the simulation result as the original data and then estimate the optimal levels. This means that we would need, for example, you already do some simulations based on maybe the geometry that you designed and also the process parameters that you assumed at the very first step. And we can use that simulation as the very basic run, and then based on that run to develop what is the the parameters to choose, the target parameters to change, and also the parameters you to control. And then based on that, it's much more easier because only if you have the very first simulation, then you can target, okay, what is out of my scope, what is out of my standard, and we can base on this target to set up the target, the quality factor for the DOE. And also in the Moldex3D DOE, we use the Takuji method to do the improvement of the quality engineering. It's a method developed by a Japanese professor, and then it would shorten the time to find out the best combination of the control factors. Because we already know if you have, for example, 3 parameters, and then if you want to optimal these 3 parameters, maybe you will have maybe 20 or 30 runs in order to find the best combination with the one after another, like trial and error. But with the Takuji method, it can decrease down to 9 rounds, then you can finish the whole estimation in the parameters. So you can use shorter calculation time to find out the best combination of the control factors. Sorry. And yeah, it's also possible for the user if they are targeting on multiple targets. For example, you also want to improve the product quality with the warpage and maybe the filling time at the same time. And then you can set up the different weightings for these 2 parameters in order to get the best combination of your control factors. And down here, you can see the interface of the DOE optimizer. Usually what we use is this one, which is the design of experiment analysis, and the optimized method is the Takuji method. So here is the workflow of it. So first thing you need to do is you need to have at least 1 run, because with that run we can know what is exactly the target we want to improve. And then after that, you can base on that run to create another run. So we can create an expert run with the right click and then generate a new run. And then you can see there, the last one is called expert run. And then you select this one and then select the next step. The second step is to select on design of experiment analysis. Select on this one and then select the next. The third thing we would need to choose is the quality factor. The quality factor is the target that we want to improve in this simulation. And in here, you can select like average temperature, bulk, center temperature distribution, shear rate, shear stress, and also, of course, the warpage. Later on, we will look into more detail in this quality factor list. And then after that, we select the control factor. The control factor, you can set up the parameters that you can control. For example, the mesh itself, the material itself, and also some parameters that we usually use in the process settings. And based on this, you can, so here is the selecting the control factor. And also we can select the number of levels, which means how many parameters you would like to try in these control factors. And the next one is we need to select the DOE dialog, like how many rounds you would like to run in the simulation in order to find the best combination of the parameters. And the last one, if you finish the settings, here will be a summary like what is the exactly control factor that you select, what is the target quality factor that you would like to achieve, and also the summary. Yeah. So in the quality factor, the setup stage, the first thing we need to set up is we need to get through the solver. The quality factor is the result that we want to solve. Yeah. So for example, I want to improve the workbench, then of course I select the workbench. Yeah. And in here you can see there's a lot of different selections. Like in the filling, we can select average temperature distribution. In like a density distribution, volumetric shrinkage distribution, or even the shear rate and shear stress improvement. And also in the characteristic, we can see that there is multiple options. The first thing is uniform best, and also there's smaller best, a larger best, and also a nominal best. If you set up the nominal best, you need to set up the target value. And you can also see on the very right side, you can see the weighting. So you can set up what is the weighting that you want to distribute to target quality factor. Yeah. So here you can see that we can select multiple quality factors in order to achieve two targets at the same time. And here you can see that with the DOE run result, we can exactly see what is the effect of the quality factor 1 and quality factor 2. So here is the result of the quality factor. The first one is the average temperature distribution. The second one is the center temperature distribution. So you can, based on this result, align this result to see if the target is reaching your target or not. And there is also possibilities to set up the linear shrinkage as the quality factor. Here we offer like a method. You need to choose two node, which is the specific point on your model, and then you set it up. You can set it up as a quality factor of the target value as a quality factor, and you can also select like smaller best or nominal best to try to achieve the target value. Yeah. And about the control factor is the items the user usually can modify in the real world. The most important thing, of course, is like the geometry and also the material. And also, it is possible to modify most of the process parameters that we have. For example, like filling time, packing time, cooling time, and also like flow rate, packing pressure, such as things. You can modify most of the settings in the control factors. And the very next one after select the control factor is the orthogonal array. So here is orthogonal arrays. Like here you can see that we can use up to 54 orthogonal array to find. Here is the, I would say this is the method of Takuchi method that we usually use, and with the different levels, with the different L numbers after the L, that means different number of runs to try to find out the best combination of your control factors. And here 9 means 9 rounds and 4 control factors and 3 levels. Or L18 means 18 rounds, 1 control factor with 2 levels, the other 7 control factor with 3 levels. So when you have more control factors, of course, you will need more rounds to find out the best combination. But also you can see that there's also some possibilities for example, if you only have 4 different control factors with 3 levels, actually you can select on the different possibilities, like more rounds, like 27 rounds, in order to find out the best combination. With more rounds, there's also like possibilities to find out the best combination more accurately, but relatively you need to take more. It would take more time in the calculation. Yeah. And the next thing is the analysis result after the DOE analysis. So there is some plot. The first thing is called the quality response. So with the quality response, and on the very left, you can see in this one here. Here is the response. And you can see that with different factors like A1, B1, and C1, here, these are the control factors that you selected. And in the y-axis in here is the quality factor that you set up. For example, in this one, I think it's more like a deformation. So you can base on this to find out if how would the control factors affect the quality factors with changing the numbers in it. And in the middle is the SN ratio is quite similar to what we have in the quality response. And also we can use the graph to show you how would the we call it a sensitivity like a response chart to see how would each parameters affect the quality factors with a more straightforward figure you can see in here. Okay, so yeah, this is it. How to judge if we achieve the target or not, you can directly see from the quality result. So for example, if you want a lower warpage, then you should select A2 as the result. Okay. So here, we also show that we support the thermoset material as the material that we use to do the DOE. And also the DOE also support encapsulation simulation, which is the IC packaging. And in the IC packaging, we support like a wire sweep index, like the total displacement, total dragging force, pedal shift. We support like total displacement and von Mises stress as the quality factor. So you can set up this as the quality factor to know, okay, what would, for example, the packing pressure will influence in the total displacement of the paddle shift. Yeah. Okay, so here is a real case study that we have in the reality. It's Acer, and it's a Global Innovation Talent Award in 2015. So this is a laptop bottom cover, and the length and the width is around 200 millimeters times 150 millimeters. The thickness is around 0.8 millimeters. So in the original design, we use this kind of fan gate to do the injection. And they found out there will be a really high shear stress around the gate region. So it will lead to some really obvious on the stress mark on the top of the cover. And this is definitely not acceptable for the producer because this is a consumer product and this is the cover of the laptop. So if customer have this part, they will definitely send it back to the producer and ask them to change it. So yeah, here is the original settings. We can see the filling time. They use the 3 different steps of the filling time with the relative lower fill rate at the very beginning and then higher flow rate to fulfill the part and a lower flow rate in order to make the pressure lower in the very last stage. And also the packing pressure is like this. And the melt temperature is around 280 and the mold temperature is like different from different side. The core side is 65 degrees, the cavity side is 55 degrees. And the coolant is 5 degrees in order to cool down the part faster. So here is the DOE setup. Because we already know that the problem is come from the stress. So what we would like to change is we would like to change the shear stress to a lower value. And also we would like to change the sprue pressure to a lower value in order to avoid like a really high pressure which would lead to the shear stress. So here you can see the weighting of it, both of the parameters is 50%. And in here, we have a different gate design. And according to the agreement with Acer, they have forbidden us to show you the real gate design. So we only use the code to show you what is the gate design here. And there is 4 different gate design in the simulation. And also there is 4 different melt temperature, 4 different mold temperature, and maximum flow rate of the melt front. So here is the result. We select 4 levels of different parameters. Each parameters we have 4 different levels. And here you can see that the result of the shear stress. So with the shear stress, for example, in the melt temperature, we can see that the SN ratio is quite high in the higher melt temperature, and also higher mold temperature. So with this kind of result, we can judge that, okay, which one is the best in each parameters. And for example, in the parameter B, maybe the better one is the B4, and also the parameter C, which is the mold temperature, the better one is the highest one. And also in the flow rate, you can see that the trend is like this. So actually the best one could be the D3 instead of the D4. Yeah. Okay. And also here is the relationship to the sprue pressure. We can see that with the mold temperature and maximum flow rate, they have a relative lower effect to the sprue pressure itself. And actually the sprue pressure is much more stronger related to the melt temperature itself. So in the theory result, we can find the worst design is like here we have like the melt temperature is 300, the mold temperature is 50, the maximum flow rate is 25%. We will get a really high shear stress and a relative higher sprue pressure. And with the best design, with the D3 gate design, and with the higher temperature in the melt and the mold temperature, and with the slightly higher in the maximum flow rate, we can get a really low shear stress and sprue pressure. So we use this kind of design to do the real test. So here is the simulation between the original design and the optimal design. You can see that we set up some nodes in order to catch the behavior in here. And with the optimal design, because we changed the shape of the gate. So it was changed to a longer one. So we put a sensor node across the gate with the same intersection, same percentage of the intersection. Yeah. Okay. So in here, you can see that the shear rate around the gate region, you can see the shear rate is quite high in this area, which is close to the end of the gate. We can also observe that the region with the high shear rate, we can easily observe the stress mark on the surface. So the target to solve is the target that we would like to solve is the shear rate around this region, which is close to the end of the gate. And here is the result after the modification. You can see that the shear rate is decreased quite a lot. And also with the real part, which is with the modified gate location, modified gate shape, and also the changed parameters, we can see that the stress mark is almost eliminated on the surface, though there's a slightly stress mark on the surface, but it's also possible for the producer to use some paint to like eliminate it on the surface. Here we can compare the original and optimal shear rate. Because shear rate, there's no value. You can directly compare. This is under the same scale, so you can see that the shear rate is decreased maybe we can say close to 10 times smaller in the highest peak value. So you can see that this is how do the DOE can help us in here. And we can also look into the more detailed result. So with the shear stress, you can see that with the original design, the shear stress is really high in the middle. You can see that. Oh, sorry. Yeah, you can see that in the very middle of the part, you can see a really, really high shear stress. And in the optimal design, you can see there is still a high shear stress around the gate because it's impossible to avoid this problem, but it's much, much more lower than before. Okay. And also in the next one, we can see the volumetric shrinkage. It was quite high at the very beginning because it was quite not really like evenly distributed in the original design, but it's much, much more evenly distributed in the optimal design. Also, in the density, we can see that because the packing effect was quite good in the very first original design. So you can see that the density is much more higher in the middle. But with the optimal design, the packing pressure is much, much more evenly distributed inside the part. So we would say that with this kind of design, it's much more better in the part design. Okay, so this is the end of this case. You can see that with the DOE design, we can directly judge, okay, which kind of geometry is the best for our product. And okay, also we can at the same time to estimate, okay, what is probably the parameters we should use in the reality to achieve the target of getting the lowest residual stress inside the part. And the next thing about the DOE is the future. And in the future, we will have a brand. I think most of you already knew that we are stepping into the new interface, which is called Studio. And we are really happy to announce that in the R18 we will have a brand new interface for the DOE in the studio, and the method is basically the same. Only the interface is slightly different. You can see in the top left is the setting of the DOE. You set up everything in one page, including the control factor and quality factor. On the right hand side, you can see the summary after the simulation. You can see how would each parameters, how each run have the result, and then you can base on this to judge if the best combination is okay or not. And also you can see directly the SN ratio and also the report, which is the diagram with the higher resolution in the studio. Okay, so this is all of our today's presentation. And here we would like to give you some summary. The first thing is that the DOE workflow is really user-friendly. And you can see that it's quite easy. You just click on next step as long as you have finished your settings in the quality factor and the control factors. And then we are able to select multiple quality factors for DOE analysis with the weighting function. And also you can several as much as the control factors that you want to select. And you can select different levels to achieve, make sure you can find the best combination of the control factors. And we can automatically generate the graphical plotted summaries in order to find out the best design much more easier, because yeah, with the digital numbers, maybe it's really easy to know exactly the number, but with the graphic, you can choose the result much more easily. And the last thing is that we will support DOE in Studio from R18. Okay, so this is all of our presentations for today.